Good morning. So in this video, I'm going to discuss the turbines. So a turbine is generally used in generating electricity. This is usually connected to an electric generator. So let me share the PowerPoint. Okay. So generally a turbine are alternate sets of nozzles and blades. So generally, steam enters the turbine. So the nozzle increases the velocity of the steam. Basically, what happens is that the enthalpy or the energy of temperature and pressure is converted to kinetic energy. So, di ba na-discuss na naman natin yung nozzle. So, ang illustration natin doon yung kamukha yung kinakabit sa dulo ng hose, no? So, pag lumabas yung tubig dun sa dulo ng hose tapos may nakakabit na nozzle, mas mabilis yung velocity ng water. So, ganun din sa turbine. Meron ding nozzle. So, pag mabilis na yung velocity ng steam, okay, tatama naman siya dun sa blade. Yung blade naman, pag tinamaan siya ng steam na mabilis yung velocity, it will result to the turning of the shaft, as you can see in this illustration. So parang LEC yung blades, ano? So iikot yung shaft. Tapos yung shaft nakakabit siya sa electric generator. So, di ba? Whenever you move a conductor inside a magnetic field, you're going to produce electricity. Ganun lang naman yun, ano? So basically the blades, no, converts the kinetic energy into shaft work. WS. Ano? So, ganun lamang yan. So, hindi lamang isang combination ng nozzle tapos isang blade din. Usually, ang turbine is made up of several nozzles and several blades, no? Hanggang maubos yung enthalpy or yung energy nung steam. Lahat makukonvert sa kinetic energy. Tapos lahat yung kinetic energy mako-convert sa mechanical energy. Tapos yung mechanical energy naman magiging electrical energy. So basically, ganun yung kwento ng turbines. So, sa Aspen High Seas, no, you won't usually find turbine. Sa chemical engineering, usually ang ginagamit nilang term sa turbine ay expander. So, sabi ni Banes, whenever steam is passing through such a device, no, the term that is properly used is turbine. Pero whenever, halimbawa, ammonia or other chemicals like ethylene gas is passed through such a device, no, this device is known as expander. So as you can see, expander kasi generally bumababa yung pressure, nung gas, ng chemicals. Yun yung difference ng turbine at saka expander. Pag steam yung dumadaan, turbine. Pag hindi steam, bawa ammonia or ethylene, expander. Tapos sa Aspen High Seas, ang tawag dyan, expander. Okay. So energy balance in turbine. So pag na gano tayo, nag-general energy balance tayo, halimbawa, i-recall natin yung equation. Diba, equation natin ay delta H equation natin, ang general energy balance equation natin is delta H plus delta KE, kinetic energy, plus delta PE, potential energy, is equals to Q plus shock work, WS. So, may imagine nyo naman, generally, horizontal lang naman ang turbine, ano? So, negligible naman yung potential energy. Tsaka, sa empirical study shows na compared to other forms of energy, sa turbine, negligible ang potential energy. Ganun din ang kinetic energy, no? Empirical study shows that kinetic energy is generally negligible, or you can equate this to zero sa turbine. No? Tapos ito namang Q, usually kasi ang una natin sinosolve muna yung yung ideal, no? Ideal na delta H, yung isentropic delta H. So pag ganun yung kaso, pag halimbawa reversible, isentropic, itong Q, nagsisiro muna. So that's why with this kind of reasoning, with this kind of assumption, we end up with delta H is equals to WS is equals to delta H. No? Okay? And then when you multiply both sides of the equation with m dot, di ba kung tandaan nyo pa, yung WS dot is equal to m dot times WS. Okay, so if you multiply both sides of this equation, you will have WS dot. You're going to multiply both sides of the equation with m dot. Ito, WS dot is equals to m dot times delta H. Okay, so dun galing yung dalawang equation na to. Ano? So basically, in order to solve for the horsepower or the amount of power, no, that the turbine will generate, you just need to find the final and the initial enthalpy and the flow rate of the steam. Ano lang naman, no? So m dot times H2 minus H1. Or simply, if you wanted to find the WS is kilojoules per kilogram, ano pag SI, the shop work, this is simply equal to delta H, or H2 minus H1. Okay, I hope you're getting this, ano? Tapos, what about adiabatic turbine efficiency? So, ang gagawin natin kasing pagsosolve, i-assume natin muna na yung process ay adiabatic, hindi siya nagpo-produce ng heat. So 100% siyang efficient. So pag 100% siyang efficient, it's the same as saying that the process is isentropic, no? Hindi yung delta S niya is equals to 0 when you say isentropic. Tandaan niyo pa? When you say isentropic, delta S is equals to 0. So ito yung maximum amount of work or electrical energy na pwedeng ma-produce ng turbine, when you assume that way. Ito yung parang pinaka 100% efficient. So pag nagka-calculate tayo ng efficiency, ang ginagawa natin, yung actual, which is mas mababa, dinidivide natin nung WS isentropic. Nung actual. Nung ideal. Actual divided by ideal. Okay. Imagine niyo, pag mas ideal, mas madaming kuryente or mas mataas yung power na mapuproduce nung turbine. So, siyempre, ang efficiency naman dapat less than 1 yan. Less than 100%. So, kaya yung actual, i-divide niyo nung ideal. Okay? So, ganun din sa delta H. Delta H divided by delta S. S here means isentropic. So, experience will tell us that the normal efficiency of turbine is from 0.7 to 0.8. Parang 70% to 80%. Sa Aspen HICs, pag hindi nyo binago yung efficiency ng turbine, ang default value na ay 0.75. Okay, so let's take a look at the graphical illustration right here. So, ito yung mga isobaric plots, P1 at saka P2. Tapos on the X, we have the entropy. On the Y, we have the enthalpy. So, generally, ito yung initial condition. We have the pressure 1 at saka temperature 1. Okay, pressure 1 at saka H1. Tapos, if it undergoes an isentropic process, so parehas lamang yung entropy, S. So, ito yung isentropic process. So, ito yung magiging H2 prime natin. H2 prime. So, as you can see, mas malaki yung delta H prime, ito yung ideal. Okay? Pero, di ba, second law of thermodynamics, the entropy of the universe is increasing. So, ito yung nag-increase yung entropy. Ano? Ito yung actual. So, as you can see, pag kinuha niyo yung delta H, mas maliit yung delta H sa actual. Ito lang, ito yung actual delta H, ito yung ideal delta H. If you divide the two, you're going to get the efficiency. Okay? So, hindi naman talaga nagsisiro ang delta S in reality. Ano? Kasi second law of thermodynamics yan. The entropy of the universe is increasing. Okay, so let's try to go to the next slide. So we have here the problem, example 7.6. A steam turbine with a rated capacity of 56,400 kilowatts operates with steam at inlet condition of 8,600 kilopascal and 500 degrees Celsius. Yung mga susunod na problem, mahalaga talaga ma-master nyo kung paano gumamit ng steam table. Ano? So part naman talaga yan ng being a chemical engineer. Dapat marunong kayo magbasa ng steam table. Basically, ang gagawin nyo lang, punta lamang kayo sa, this is an SI units, ano? Punta lamang kayo sa superheated, no? Part. So, hanapin nyo lamang yung, una nyo hanapin yung pressure muna, 8,600 kilopascal. Tapos, hanapin nyo yung temperature, corresponding temperature. Usually, pag turbine, ang hinahanap dyan ay enthalpy at saka hinahanap yung steam table, ano? Enthalpy at saka entropy, yung H at saka yung S. Corresponding to these two conditions. Tapos it discharges into a condenser at a pressure of 10 kPa. Okay? So ang gagawin nyo, i-assume nyo lamang na isentropic yung process. Kung anong nakuha nyong entropy dun sa pumasok na steam, i-assume nyo, yun din yung entropy dun sa output, no? So you have two conditions now. Itong 10 kPa na pressure at saka yung S2 na S2 prime equals S1 prime. So you'll be using that to find H2 prime, no? Kasi basta naman meron na kayong dalawang condition, you can find the other thermodynamic property. Okay? Tapos pag nakuha niyo yung H2 prime, H2 prime is the ideal enthalpy, ano? Hindi pa yun yung actual. So para makuha niyo yung actual, gamitin niyo yung efficiency equation. Tapos given yung turbine efficiency na 0.75, makukuha niyo yung actual delta H. Or actually, pwede niyo ring makuha directly yung actual H2. Ang tinatanong kasi dito is determine the state of the steam at discharge. Kailangan nyo kunin yung actual H2 tapos gagamitan nyo ng quality equation para makuha nyo yung X. No? Tapos yung mass rate of flow of the steam, ito yon. Gagamitin nyo to. Diba? Ws dot is equals to m dot times delta H. So, meron na tayong delta H kasi nakuha na natin yung H1 tsaka H2. H2 actual. We can now calculate m dot from the rated capacity of the turbine. Na? So, ganun lang. Mahalaga dito, mahanap niyo yung marunong kayong gumamit ng steam table. Okay? So let's start. So ang turbine, we draw it this way, ano? So, ito pumapasok. Ito yung, ang P1 ay 8,600 kilopascal. Tapos ang P2, ang T1 ay 500 degrees Celsius. So just use your steam table and then try to find H1 at saka S1. So S1 is 6.6858. So this is kilojoules per kilogram Kelvin. Tapos H1 naman from steam table is 3,391.6. Okay? Tapos ang final pressure na lumalabas sa problem ay 10 kPa. Okay? So, i-assume muna natin na isentropic yung process. So, pag isentropic yung process, yung S2 prime ay equal sa S1. This is also equal to 6.6858. So with this, we can try to find the quality. Usually, paglabas ng turbine yan, wet steam yan. Generally, ganun yung kaso. Papasok siya ng superheated, tapos paglabas na wet steam. So, ang unang hinahanap dito ay yung quality ng wet steam. So, generally, if we're going to go to 10 kPa, makikita nyo, itong 6.6858 is between SL and SB. No? So, yung ang SL natin at 10 kPa ay 0.6493. Tapos ang SB ay 8.1511. Diba? Yung S2 prime is in between these two values, no? Tapos makikita niyo sa steam table yan, pataas na, pag superheated na, mas mataas na sa 8.1511. So definitely wet steam yung lumalabas sa turbine. So then next you're going to use the quality equation. Dahil niyo pa ba yun? SL times 1 minus X plus SB times X. So substitute nyo lang yung SL at saka SB, saka yung S2 prime. 6.6858, tapos SL 0.6493, plus 1 minus X. X is unknown. Tapos plus 8.1511 times X. So solve X. You're supposed to get something like 0.9377. Okay, so with this, you can now solve H2 prime, no? So ganun din, kukunin niyo rin lamang yung HL at saka HB sa steam table. So from the steam table, HL is 191.832. Sorry, this is not 0.9377. This is 0.8046. So HL is 191.832. And then HB is 2584.8. Puro SI naman to, ang unit yan, puro kilojoules per kilogram. Tapos yun, you can now calculate H2 prime. So H2 prime is simply HL 191.832 times 1 minus X, 1 minus 0.80.46. Tapos plus HB 2584.8 times 0.8046. So H2 prime is 2117.21. So this is in kilojoules per kilogram. Okay, if you have this value, you can now calculate delta H prime. Diba? Delta H prime is simply equal to H2 prime final minus initial H1. Itong H2 prime, ito yung enthalpy ng na nag-result sa isentropic process. No, constant yung entropy. So hindi ito yung actual. Ito yung ideal, Just substitute the values. So delta H prime is H2 times 2117.21 minus H1 na 3391.6. So delta H prime is, you're supposed to get something like diniretso ko na kasi sa ano the equation, ano? 2117.21 minus 3391.6. You're supposed to get something like negative 1274.39. 39. Of course, this is still in kilojoules per kilogram. Yan. Tapos, i-recall nyo, kailangan nyo i-recall yung equation ng efficiency ng turbine. Siyempre, equation ng efficiency is actual divided by ideal, delta H. Ano? Substitute natin, given na 0.75 ang ating efficiency. Tapos hanapin natin yung actual, yung delta H. Yung ideal is negative 1274.39. So, ang actual delta H is 900 something. Negative 955.17. Ayan, basically with this delta H, we can now calculate the actual H2, no? So after calculating the actual H2, you can use that to determine the state of the steam discharge, yung quality niya, ano? So, diba, delta H is equals to H2 minus H1. Substitute nyo lamang yung value, negative 955.79, and then H2 is unknown. H1 minus, H1 is 3391.6. So therefore, H2 is 2435.3. So pag nakuha nyo na yung value ng H2, you can now calculate the the quality. So basically parang ganito lamang equation niya, ano? You just substitute the H2 right here. Ito itong H2 na to. Substitute ko lang dito. Same equation, quality equation. Tapos ito pa rin diba? Ito yung sa 1 atmosphere, ano? So ito pa rin naman yung ating HL, ito pa rin yung HB. Ang mangyayari lamang diyan, ito, syempre, mapapalitan to. So we have here X and then another X. And then you just try to solve for X. So the final quality of the actual process is, we're supposed to get something like 0. Kanina, 0.9377. So yun yung final quality. Okay, so I hope you can follow the flow of the solution. Ano? Tapos the other question is the mass rate of flow of the steam. Ano? Medyo marami nang makasulat. Pero kung hanggang dito nasundan niyo naman, okay na. Ito madali na lang to, itong mass flow rate of the steam. Nagamitin niyo lamang itong 56,400 kilowatts. So this is WS dot. Tapos this is equal to M dot times delta H. No? So yung delta H natin ito. Equate niyo lamang itong dalawa, tapos kunin niyo lamang. Basically parang kunin niyo lamang yung 56,400 kilowatts divided by negative 955.79. So lalabas na din yung kilogram per second ng steam. Ano? Itong dalawa. Okay? Ganun lang yung kasimple. Parang ano rin yan. WS dot is equals to M dot times delta H. Ito dapat yung actual. Ano? So it's 56,400 M dot simply equal to 56,400 all over 955.7. So huwag nyo nang include yung negative kasi magiging negative yan. Wala namang negative na flow rate. Ano? So, syempre alam niyo naman yung sign naman dito, ano lang naman 'yan. Convention lang 'yan. Kasi actually ang totoo niyan, pag sinunod natin parehas yung convention, itong 56,400 negative 'yan. No, yung output ng turbine negative 'yan. Tapos itong negative din. Kaya magiging positive yung tanda. Yung ano? You're supposed to get something like 59 kilogram per second. Ito yung second panel answer. So, I hope you get this one. Ano? Okay. So, kindly answer the exercise after this video. So, hanggang dito na lang muna to. So, in the next video, I'm going to discuss the compressor.